everybody. So today we're going to be discussing properties of logarithms, and this section is a continuation of the previous section. So last section we introduced the idea of logarithms, and now we're going to talk about a few properties of logarithms that will help us simplify and rewrite logarithms in our favor. And in particular, I wrote down 5 rules in the notes. There's going to be 3 that we're really going to take emphasis with, and that will be the product, the quotient, and the power rule. The other 2 are miscellaneous. They don't really come up for the remainder of the semester, but there's a few problems in this section that will utilize those 2. But as I mentioned, the product rule, just to motivate the namesake of all of these, the product rule is referring to whenever you have a product that is being evaluated by a logarithm. So if you're taking the logarithm of a product, then you are allowed to split the logarithm into 2 separate expressions, where the first part of the product gets 1 log and the other one gets another log with the same base. But we can actually use this idea in the converse direction. If you have 2 logarithms that fit this format, we can combine them together to be 1 logarithm. And we'll look at examples that utilize both directions. Quotient rule, it's very similar, but instead of a product, of course, there's a quotient. And instead of a plus sign, we have a minus sign. So this gives us ideas on how to combine and split up various logarithms. We also have something called a power rule, which I think is fairly straightforward. If you are evaluating an exponential function in your logarithm, then any exponent can be brought to the very front of the logarithm. So notice this exponent here, this r, comes to the very front, and notice no more exponent. So these first few problems we're going to evaluate will start to motivate some of these rules. So let's go ahead and start off with the first one here. So when we look at these problems, something to keep in mind is what type of function, what kind of expression are we looking at whenever we're evaluating a log-based problem? Is the log evaluating a product, a quotient, or a power? So we look here, is the log evaluating one of those 3? Yes, an exponent. This is an exponential function. So that means that, well, the power rule is pretty helpful here. And so the power rule, and in fact, what I like to do is I like to circle the exponent and use an arrow to indicate where the exponent is going. So that tells us, if we follow the power rule here, all that simply tells us is that we can rewrite this logarithm just like this. And from here, now we can try to evaluate this log base A of A. And we simply have an r times whatever the output of this is. So the r is just, this is multiplication here. And so you might think, well, what's log base A of A? It's a bunch of symbols. Well, we do have a way of rewriting logarithms, that way being so this was a part of that calculator-friendly version that I mentioned in the last section. The problem technically says don't use a calculator, but I will encourage and recommend a calculator for anything you can evaluate, as we'll see in the next few problems. But here we have log base A divided by log base A. What is anything divided by itself? Well, that's just 1. So this fraction here actually goes to 1, and there's an r in front, so it's r times 1. And r is the correct answer here. So this is technically another property that we just kind of derived. So you can use this property as much as you want, but that is the motivation behind why this property is true, why the a's virtually cancel, and why the exponent remains as the final answer. So let's look at an example of actually part 1 here. We move on to part 2. If you were to use that exact property, well, that would tell you that these 5s virtually cancel out and you get 38. But maybe you didn't realize that immediately. So what you can do, we are evaluating an exponential function, which tells us that you can bring the exponent to the very front. So that would tell you 38 log base 5 of 5. So 38 times log base 5 of 5. And from here, log base 5 of 5, you can look at it the same way we did here by rewriting it in a calculator-friendly version. And log of 5 divided by log of 5, that is in fact 1. So then we just have 38 times 1, which is 38. So you can either remember the formula or just derive it this way. It's up to you. Move on to problem 3 here. So here, well, here's the natural log and the e stuff. There's actually 2 ways you can do this problem. I'm going to do it the longer way first. So natural log does have the same properties listed here. Remember, a natural log is simply a special type of logarithm. It's so special that we give it its own special notation, ln. And so from here, one way we could do this is figure out how a natural log is associated with a logarithm. So that would tell us ln stands for log base e of e to the negative 15. So that's all ln stands for. It's just log base e of whatever follows. And if you do it that way, you end up finding out that this conforms to the same types of problems in 1 and 2. And that would end up giving us negative 15. By the same logic, you would bring the negative 15 to the front, divide log of e divided by log of e, just like we did here. So you would just replace all the 5s with an e, for example. And so negative 15 would be the correct answer. Now I did mention there is a more simplistic solution. And this is going to be helpful in this section and the next section. So natural log and e are inverses of one another. So whenever they're next to each other, if you're taking the natural log of e, they are inverses, which means they cancel out. So another way you can look at this problem, if you're evaluating ln of just an e function, they cancel out because they're inverses. And you're left with negative 15. This is an idea we're going to talk about more when various ln problems come up, but ln and e are inverses, so their mere presence next to each other will resemble a cancellation. Just like how square and square root, whenever they're next to each other, they cancel. We'll move on to problem 4 here. So notice we have 2 logs that are being added together. So if you were to try and evaluate this in your calculator, log base 18 of 6. And so you can actually do that. I'll do this off to the side. So if you were to try and put this in your calculator, what you will end up getting, so let's see, log of 6 divided by log of 18, you're going to get a really, really messy decimal. In fact, it doesn't convert to anything. If you try to turn it into a fraction, it's not going to work. So the answer here is an integer, is a whole number. But you will get nasty decimals from both of these individually, which motivates us wanting to combine them together. So adding logs Well, what does it mean to add logs? Which one of these rules does this conform to? And we notice the product rule. It has criteria for when you're adding logarithms together. What it says is those logarithms can be combined into one logarithm. So here we can combine this into one logarithm. And notice the base just carries over. This is one logarithm with the base carried over. And so what's inside the logarithm? Well, the product rule tells us, well, it's a product. Here's the 6 times the 3 over here. So that's it, that's the application of the product rule. Now let's go ahead and simplify this. This is log base 18 of, actually 18. And as we've already seen before, from parts, well, 1, 2, and 3, log base any number of itself is just 1. Or you can throw that in your calculator. You might want to do that just to make sure you can, and you would get 1. So that would be the answer here. We'll move on to example 5, which instead of a plus sign, there's a minus sign. So instead of the criteria involving adding logs, we're going to use the one that involves subtracting logs. So there's a minus, so we use the quotient rule. So this tells us, so it starts off the same way. The log base 6's just combine together, and what's inside the logarithm is the quotient. Now, the order does matter. 42 divided by 7 or 7 divided by 42, that order matters. The positive log has to go on top. So the positive log is the one with the 42, and that's why it's here in the numerator. 7 denominator, so that order does matter. But now we can evaluate it. 42 divided by 7 is 6. And we have log base 6 of 6, which, as we've seen in every example so far, that's just 1. So we've talked about the product rule, the quotient rule, and the power rule. Let's go ahead and look at problem 6 here. So problem 6, the exponent of problem 6 does conform with one of our rules. So if we were to evaluate this, let's look at the exponent individually. We'll just let the 7 carry over for now. Log base 7 of 1 minus log base 7 of 2. So you can do this in one of 2 ways. Well, if you were to try and evaluate log base 7 of 1 and log base 7 of 2, you would end up noticing that one of them you get 0, and the other one you get a really messy number. Let's go ahead and utilize the subtraction here, which resorts to the quotient rule. So what that would end up being, we can combine these 2 logs together to get one logarithm with the same base. And then the quotient would tell us, well, the 1 goes on top and the 2 goes on the bottom. And so all of that, just because of the problem, it was in the exponent when we started, it's still in the exponent now. So finally, we look at this and we notice this is actually one of those miscellaneous rules. Notice it's right here. It's a base raised to a logarithm. And this is the only example I've found, other than restating the definition, where I've seen this problem. So this says if you have an exponent where the 2 bases are the same, then what we're evaluating is the answer. And outside of this problem, I'd say don't really focus on that miscellaneous rule too much. But other than that, that's a few examples of evaluating logarithms given the properties of logs. So what we're going to look at now is expanding logarithms from 1 into 2 or more, and this allows us to simplify logarithmic expressions. So we'll go ahead and start off with the first one from example 2. And with this problem, so we're expanding it. So if we look at our rules over here, we have different ways of expanding. And so what it wants us to do is figure out what rule that this applies to. So the logarithm, we want to figure out, is the logarithm evaluating a product, a quotient, or an exponent? And I think that one's pretty clear here. It's a product because we have 343 times x. There's no exponent, there's no quotient, so this one seems pretty straightforward. And if we follow the criteria for the product rule, so we're going this direction. It says if we have a product, then each number or each expression in the product gets its own logarithm. So 343 is going to get its own logarithm. And then plus, and x gets its own logarithm. So just like that. And notice it's the same base, it's just we're splitting up the logarithm. And now notice, so for this term here, we cannot simplify that anymore. There's no exponent, there's no product, there's no quotient. This one's done. However, over here, we have all numbers, which means we can actually try and simplify this. So we can try and see how this looks in the calculator. And so if we were to attempt to put this in the calculator, so remember the calculator-friendly version looks just like this. And if you were to put that in your calculator, so let's go ahead and see what that comes out to be. Log of 343 divided by log of 7. So I'm just putting this fraction in the calculator and I get 3. So make sure you can get 3. But we can simplify this fraction here. And then the log base 7 of x just follows. And that would actually be the answer for the first one. And when we move over to the second one, we again ask ourselves, is the logarithm evaluating a product, a quotient, or an exponent? Now you may notice that there is an exponent and a quotient in this problem. So, and you can have problems that have more than one rule, that utilize more than one of the rules. In fact, we have some problems that utilize all 3 of them. So we have to break it down as, well, is this whole expression here, is it a fraction first or an exponent first? And it's a quotient first, it's a fraction, because the whole fraction is not being raised to a power, it's a fraction that has an exponential function in it. So that's kind of the distinction. We'll look at a few more of these as we keep going, but you definitely want to identify that this is a quotient. So this is a quotient first. The quotient rule tells us the numerator gets its own logarithm and the denominator gets its own, separated by a minus sign. So that tells us precisely what to follow. So the numerator goes first. The quotient rule tells us to put a minus. And now the denominator gets its own. And notice it's the same base of the logarithm. Now we have 2 different logarithms to look at. So there is a part of the problem that says express powers as factors. In essence, what that means is express any exponents as, well, it wants us to utilize the power rule. So in this case, we do have a power, so we're treating this logarithm separately, we're ignoring this one for now. And so with this one here, it says if you have any powers, if you're evaluating an exponential function, bring those powers to the front. So I'm going to utilize this little way to help me remember what to do. This 2 now comes to the front of the corresponding logarithm. And for this logarithm, we get 2 log base 9 of x. Notice the second power is up here, so I don't have to write it here. But we still have this over here. And so that's all numbers. So this is all numbers. We can try to figure out what this means in the calculator. Remember the calculator-friendly version of this expression? Would work out just like this. And so log of 81 divided by log of 9, you should get 2, but let's go ahead and verify that. Log of 81 divided by log of 9, you just get 2. So our final answer will be minus the 2 that we just found, minus 2. And that would be the answer for the first two. So for the next two, we have two natural log based problems, and they are, even though they look similar, there's actually more complexity to problem 4 than you think. So let's go ahead and look at problem 3 to compare where this complexity may lie. So this one here, so we still think about it the same way. Now remember earlier, I did mention if there's a natural log and an e next to each other, if you're evaluating an e function with a natural log, then the e and the natural log cancel. Notice that's not the case here. It's not just ln and an e. That x is getting in the way, which is another reason why splitting up logarithms is sometimes a good thing, because we can simplify individual components after we split everything up. So we look at this, and we compare this to the rules we have. So there's a product, x times e to the x, but there's also a power, e to the x. So there's two rules at play here. We got to figure out which one to use first, because that does matter. And so we look at this as, is this an overlying product or an overlying fraction, or not fraction, an overlying exponent? And it ends up being a product because, I think similar to problem 2, the whole expression here is not being raised to a particular power. So here we're using the product rule. So each part of the product gets its own natural log. And I can't remember if I mentioned this, natural log shares the same properties as the logarithm. So you do get a product rule, a quotient rule, and a power rule with the natural log, as we'll find out from some of these problems. So we do apply the power rule, or product rule rather. So this leftmost expression is done. There's no products, quotients, or exponents. Over here, there is an exponent. And so we can go ahead and either move the exponent to the front, or you can actually cancel out the ln and the e. It ends up resembling the same thing. So what we can go ahead and do is emphasize so again, this is whenever you have just a natural log and an e next to each other. If you're evaluating an e expression, those two cancel out. We couldn't do that before because the x was getting in the way, but there's no x to get in the way, and that exponent is part of this e term. So now this simplifies as ln of x plus the exponent, which just simply drops down, just like that. And this would be our answer for 3. So problem 4, this is a good motivation to problem 4, because problem 4, I noticed a lot of students last semester, they saw the ln and the e next to each other, and they canceled out immediately by the same logic they saw here. But there is a huge difference between this term and this term. Here the x is an exponent, and this x, well, is not an exponent. This is a product here. This is a sneaky problem, just merely off of that premise. So that's why I wanted to show you all. So instead, so as I mentioned, it's a product which conforms to the product rule. And that tells us that each part gets its own natural log with a plus sign separating them. And now here, we do have the natural log and the e right next to each other, which means they cancel. They don't cancel and disappear entirely. Instead, they yield a 1. So they don't just cancel and disappear. It acts the same way as 3 divided by 3. It doesn't just disappear because the 3's cancel. 3 divided by 3 would give you 1. So same idea here. The ln and the e, if there's nothing left over, if there's no exponent, well, the exponent's understood to be 1. So that's kind of the thought process here. This would be your answer. So finally, we'll go ahead and look at problems 5 and 6. So with problem 5, we again ask ourselves, are we taking the natural log of an exponent, a product, or a quotient? Well, there's definitely no quotient, but there's actually 2 powers. We'll get to the second power in a second, but there are exponents occurring, and there is a product occurring. X to the 8 is being multiplied to the square root. So we have to think about the bigger picture. Is this an exponent first or a product first? And the answer is that this is a product first, because this whole expression here is not being raised to any one power. So this is a product rule. We will be using a product rule where the product is happening right here. The product rule tells us that each individual part gives its own natural log. But then we also have to, as the problem states, express any powers as factors, which means any exponents have to come to the front. So, exactly that. So for this problem, we have ln of x to the 8, that is in fact an exponent. So that means that this comes to the front. Oops. Over here though, so it may not look like it, but a square root function is a power. And maybe you do or don't remember, it's been a while since we looked at it. The square root actually represents the 1/2 power. So we're going to rewrite this as the square root, instead of the square root of 7 minus x. Remember, the square root means the 1/2 power. And my math lab will make you identify this so you can bring the power to the front. So this is something you definitely need to identify moving forward. But once you do, now you know that the 1/2 power can come up to the very front. And notice this is only coming to the very front of the corresponding logarithm. This 1/2 is not coming to the very front here with the 8. It only goes in front of the term that it corresponds to. But other than that, we've evaluated all the products, quotients, and exponents. There's nothing we can do here that's not a product, a quotient, or an exponent. So we can conclude with this as our answer for number 5 here. Now number 6, as you can tell, this one's probably the more complicated of all the problems. It involves every rule, and it is a fairly intricate problem, so let's go ahead and talk about it. So we look at this mess and we try to break it down one step at a time. There's definitely a quotient, there's an exponent, there's another exponent. What we have to look at is, are we taking the natural log of a product first, a quotient first, or an exponent first? You might be tempted to say it's a quotient first, but notice that whole fraction is being raised to the 1/5 power. That means that this whole thing is really an exponent, and we have to bring that exponent to the front first. So this is an exponent. We bring it to the front using the power rule. And so now we have 1/5 natural log of, well, everything else. Now we apply the same idea. Are we taking the natural log of an exponent, a product, or a fraction? And it turns out here we're taking the natural log of a fraction. This whole thing in here is a fraction first, and all the other rules are within the fraction. So now we're going to use the quotient rule. And something to notice, I'm going to put the result of this in parentheses. I'll explain why in a second. But remember, the quotient rule says the numerator gets its own natural log, and the denominator does, with a minus separating the two. And I'm going to close this parenthesis. The reason why I kept all of that in parentheses is because this 1/5 out here is being multiplied to whatever the result is. So that 1/5 would have to distribute to everything. It can't just be left on this term. So that's why I'm putting everything in parentheses, because that 1/5 multiplies to everything. And so from here, we want to, well, this isn't an exponent. This isn't an exponential function. We cannot take that 2 and bring it to the front, because this whole expression is not an exponent. However, we can still simplify this. And this is a quadratic. What do quadratics normally do? They factor. So, if you can identify the factorization, the factorization seems to be x minus 3, x plus 2. If you can identify that factorization, then you realize, well, that's a product rule. We're taking the natural log of this product, which means we can apply the product rule to that. For this expression here, this is the power rule. So notice these logarithms, they break up into smaller pieces, but we have to treat each piece individually, applying the corresponding rules that we find. But let's go ahead and evaluate this. So as I mentioned, this whole first term can be rewritten as this. And since this is a product rule, we will in fact apply the product rule. That means x minus 3 gets its own natural log with a plus sign, because now x plus 2 gets its own. So that was all of this, and minus the 3 that we just moved to the front, the exponent. We'll close that parenthesis for the 1/5 to multiply to everything. And this is actually our final answer. There's no more exponents, there's no more products or quotients. So we would conclude this as our final answer. So now what we're going to do is work in the converse direction. So instead of taking one logarithm and splitting it up a lot, we're going to take split up logarithms and reduce them down to a single logarithm. And we'll go ahead and start off with problem 1 here. So this will be using the product, quotient, and the power rule in the opposite direction. So we are considering any sort of sign indication, as well as moving around powers. And so you might notice a plus, which would imply that we would use the product rule. However, one issue with that in this current form is that these not exponents, these numbers in the front are getting in the way. So what we would have to do first is, well, move those numbers as powers. And the way we do that is the opposite of what we did before. So we take any number in front, the 2, and we bring that as the exponent of the corresponding logarithm. We don't bring it to the very back. We bring it to whatever that current logarithm is evaluating. And so same with the 7 here. The 7 will be applied to the exponent of v in this case. And so what we get is log base 6 of now, so this is u, it's going to be u squared, because we are moving the 2 as the exponent, plus, and we just moved the 7 here, log base 6 of v to the 7. So the only reason we did this is so we can get the logarithms by themselves with no numbers in front. And that way, the product rule comes into play nicely. Notice this product rule does not have numbers in the front, and we want to resemble that as closely as possible. But now that we have that, we can go ahead and combine these logarithms as one log by using this product rule. So we're going in this direction. If we have 2 logarithms added together, then what the logarithms are evaluating come together as a product. So u squared times v to the 7th. And so we have succeeded in getting a bunch of logs as a single logarithm. The problem does say express powers as factors, but that's only if the expression we're evaluating is an exponential function. Here, it's not an exponential function, it's a product of 2, so there's no single exponent to bring to the front. So we can actually conclude with just this here. An example opposite to that idea, we'll actually see that in problem 2 here. So we go ahead and look at this, and well, there's no numbers in the front, so we can go ahead and use the quotient rule. That's what the minus represents here. So the minus rule, or the quotient rule, tells us we can combine these as one logarithm, and that logarithm will now be evaluating a fraction where the square root of x will be in the numerator and the x to the 4th is in the denominator. Well, it turns out we can simplify this fraction. These are 2 x values, and we can use properties of exponents to simplify this further. It may be kind of hard to see the evaluation in question, but remember, the square root of x is the same thing as x to the 1/2. And the only reason I emphasize that is because one of the law of exponents is we can combine these two. So this is actually just an algebra. This is just a property of algebra in general. But this is x raised to the 1/2 minus 4. So whenever you have a variable divided by a variable with the same base, you subtract their exponents. So this is a law of exponents here. And so 1/2 minus 4, if you were to plug that into your calculator right quick, you would get, I think, -7/2. Yeah, so you get -7/2. But it does say express powers as factors. And since this is the log of an exponent, that means we can take the exponent and bring it to the very front. Before, we didn't have a singular exponent to bring to the front, but now we do. And we're going to utilize that right here. So we're taking this -7/2 and bringing that to the very front of the corresponding logarithm. So -7/2 comes to the front. Everything else we write down. And you can put the parentheses if you want to, or you don't have to. My math lab won't count it off either way. All right, so we'll go ahead and look at 2 other problems, 3 and 4. So we start off by, the premise is we're trying to get all the logs to become 1. We see that there is a difference of logs because there's a minus sign, and that would normally fall under the quotient rule. However, there's these numbers in front. So we need to move those as exponents to their corresponding logarithm before we can combine. So that 2 would go to the front of this logarithm here, and this 1/2 would come to the front here. Now you could take the minus sign with the 1/2, but then you would put a plus sign here. Whatever you end up doing, it works either way. I'll just go ahead and bring the 1/2 and keep the negative. So when we go ahead and apply all the corresponding exponents, we get log base 5 of now p squared minus, and there's no more 1/2, so we have log base 5 of 25p squared, all of that to the 1/2 power. Now one thing I want us to notice here, so 1/2 power, that means a square root in this case. And that actually, we can actually apply a quick law of exponents property. That property being, well, this means square root, and we're taking the square root of a product of things, which ultimately means we're taking the square root of 25 and p squared. The square root, so 25 to the 1/2 is the same thing as the square root of 25. That's just 5. And p squared with a square root, well, the square and the square root cancel. We just get p. So we are applying a law of exponents. In fact, I did jot this one down in the notes for exponential functions. So we went ahead and applied that one. And with that simplification, we can go ahead and, well, apply the quotient rule here, which says if we have a difference of logarithms, we can go ahead and combine them together as one, but we have a fraction. So p squared is in the numerator, and the 5p is in the denominator. But technically, we're not done, because from here, what we have to do is, well, simplify the fraction, which simply means that there's a p squared and a p. So there is a cancellation. One of the p's in the numerator cancel, and the p in the denominator does as well. So now what we're left with is p divided by 5. And this is now a simplified singular logarithm. And so you might notice this is one of the workbook problems that I assigned. So if you have this answer, that'd be perfectly sufficient. And we move on to problem 4, which is again another workbook problem. And so there's no numbers in front, so we're good there. We can go ahead and use the difference to combine these logarithms together. So now we get a single log base 3. The minus sign tells us that the x squared plus x minus 6 goes in the numerator, and the x minus 2 stays in the denominator. Now this is not fully simplified. In fact, we saw a problem before where the quadratic, we ended up having more simplification behind the scenes, because whenever we see a quadratic, we think, well, how does it factor? So if we consider the factorization of this quadratic here, this factorization ends up being, plus. So, my fault. That should be a plus. So the factorization would be x plus 3, x minus 2. And so by identifying this, you notice that there's another x minus 2 in the denominator here. So they actually cancel. So those actually cancel. So this is why it's important to identify any quadratics and see if they factor, because sometimes there's some underlying simplification you need to make that my math lab will force you to make. So this would be log base 3 of just the x plus 3 that remains. And there's no powers to express as factors, so that would be sufficient for this answer. So finally, for example 3, we're going to look at these two, and we'll start off with this one. And again, we want to combine everything as a single logarithm. We can't do that immediately here because that 6 is getting in the way. We don't want any numbers in front of the logarithm. We don't want any coefficients ultimately. So we're going to move all of those as exponents. I'll go ahead and use just the 6. Bring that to the exponent of the corresponding logarithm. This one doesn't have a number in front, so that one's fine. So we can go ahead and jot down this one. The 6 here is now the exponent. And so now that all the numbers are cleared in the front, we can now apply the quotient rule. Quotient rule is whenever we have a subtraction or a difference between two logarithms. So let's go ahead and do that. Now this becomes a single logarithm where the x squared minus 25 is in the numerator and the x plus 5 to the 6th power is in the denominator. From here, you may remember the point I made just a problem ago where I said any quadratics, you might want to consider their factorizations. And here, there's no exception because x squared minus 25, you definitely need to identify that that is a difference of two squares. And by identifying that, you notice that the numerator is now x plus 5, x minus 5, and in the denominator stays the same. So just like that. And from here, there are two x plus 5 terms, one in the numerator and one in the denominator. So there is a cancellation here. One of these x plus 5s cancel with, well, they cancel out one of the 6 x plus 5s down here. So that 6 gets canceled out, but it becomes a 5 because we took one away from that. And so after we go ahead and apply that cancellation, we get x minus 5 in the numerator and x plus 5 to the 5th power in the denominator. And we ask, are there any powers to represent as factors? Because we do have this as a single logarithm. We don't want to break it up. The problem wanted us to make it a singular log. You might look at the 5 and think, can you bring the 5 to the very front? The answer is no. You can only do that if the whole expression is an exponential expression. Here, this whole expression is a fraction that happens to have an exponential function in it. So try not to confuse those two ideas. So this would be sufficient as an answer. And you cannot bring the 5 to the front unless it was just x plus 5 to the 5th power. So we'll go ahead and move on to problem 6 here. And same premise as before. Can we combine them immediately? We cannot, because there's numbers in the front that get in the way. So let's go ahead and bring those numbers as exponents. So now we have 8x to the 4th, all of that raised to the 4th, because we just brought that 4 as an exponent. So minus log base a of 4x plus 17 raised to the 1 over 8 power. Now there's not really much we can do with the 1 over 8 as an exponent. We'll just kind of leave it as such. The 4th power though, we can apply this to the term inside. The reason this one's different is because everything in here is multiplied, but this one has a plus sign. That makes a huge difference here. So that means we can use actually the same law of exponents that I used before, which tells us that 8 gets a 4th power and x to the 4th gets a 4th power. And so 8 to the 4th power, I'm pretty sure that's 4096. It's 4096. So 8 to the 4th power is 4096. x to the fourth raised to the fourth, that's another law of exponents that I talked about in that section. You multiply the exponents together, and so you get x to the 16th, because you multiply the exponents together. And so minus log base A of 4x plus 17 to 1 over 8. Now that we have the logs cleared of any numbers in the front, now we can go ahead and apply the quotient rule, because there's a subtraction or a minus sign here. So now all of this becomes a single logarithm. And we can go ahead and apply the fraction here. And then you ask yourself, okay, are there any exponents you can bring to the front? Are there any powers you can express as factors? Can you bring this 16 to the front? The answer is no, because the overlying function that the logarithm's applying is to a fraction that happens to have exponents in it. So this would actually, it's going to look very messy when you type this into my math lab, but this would be the accepted answer by my math lab. So finally, we're going to look at this composition-based problem. So we talked about composition of functions. I think it was the section right before test 3. And so there's another problem that, well, applies that idea. So if you remember, so we're going to go ahead and look for f composed with g, which means that f is the outer function, g is the inner function. So the way composition works, you start off with the outer function, so f is the outer function. We go ahead and write that down, but for every x that we see, we're just going to put parentheses as a placeholder. What goes into the parentheses is not x, but whatever the inner function says. So the inner function here is, well, g, which happens to be e raised to the 5x. So this would be the start of the composition function. However, you may notice we have natural log of e raised to some stuff, and it turns out natural log and e, they cancel, which yields simply 5x. So it turns out 5x is the composition here after everything is simplified. And we move on to find the domain of the composition. But remember, the domain of a composition, it's not as simple as looking at the simplified answer. This is just one part. So the domain of the composition, well, there's no fractions, there's no square roots, there's no logs, there's nothing crazy. The domain from this is all real numbers, because there's no fractions, square roots, logarithms, nothing we have to worry about. Another part of the domain we have to think about, though, we also have to take into consideration the domain of the inner function. That's just one of the properties of composition of functions. You have to look at the final result and the inner function. The inner function was e to the 5x. That's an exponential function, and the domain of any exponential function is all real numbers. So this gave us all real numbers, and the inner function gave us all real numbers. So guess what? The domain is all real numbers. Just like that. Let's go ahead and move on to part B here. So it just switches f and g. So here, the outer function is, well, g, which means we're going to go ahead and write out the outer function. So that's e to the 5x. But instead of x, we're going to put parentheses. And what goes into the parentheses is whatever the inner function is. F is the inner function, which is ln of x. So just like that. And you can put parentheses, or you don't have to. It's up to you. Now we have e raised to the 5 ln of x. And here we have, just like how ln and e cancel in that order, We can also have e and ln cancel, but they have to be right next to each other. Here, the 5 is getting in the way. Now I'm going to go ahead and remove all these parentheses to make it clear. But notice what happens. We have 5 ln of x, and guess what? That's a power rule. There's a power rule we can utilize here. In particular, we can move that 5 as an exponent of the x here. And what we get is e raised to the ln of x to the 5th. And the reason why I did that, I mean, I could have done that arbitrarily, but the reason why is, well, e and ln are right next to each other. So guess what? They cancel. Just like that. And we are left with simply x to the 5th. Which that would tell us is our answer here. Now we move on to the domain. Now remember, the domain, as I mentioned in part A, the domain of any composition, we have to take 2 functions into consideration. What's the domain of the composition itself? That would be the x to the 5th. X to the 5th doesn't have any fractions, it doesn't have any logarithms or square roots, so this domain would be all real numbers. However, we also have to consider, for any composition of functions, for their domain, also have to consider the domain of whatever the inner function was. The inner function here is f. So f here is natural log of x. Now what's the domain of the natural log of x? That is, well actually that's part of our parent function. That's 0 to infinity. So if you go back to the previous section and look at various characteristics of logarithmic functions, you will see that the domain is 0 to infinity. And that is what we're utilizing here. That is something you need to know. But that would be the answer for part B. And for part C, they simply say, take the f of g function, which we actually already found over here, and plug 7 in for x. So it just wants 5 times 7, that's it. So it's simply just 5 times 7, which is 35. And that's actually the answer for part C. Now we're going to go ahead and move on to parts D and E. So we'll move on to part D, which wants us to find f of h of x. So remember, the outer function is what we start to write down. So that's ln of x. But we don't put x, we put parentheses. Because what goes in the parentheses is the inner function. Whatever h is, it just says put x squared. Now there's nothing really to do here. You can bring the 2 out to the front, but this problem actually doesn't specify. It doesn't ask you to bring powers as factors. So you can actually keep this answer. There's nothing to do. And we look for the domain. The domain, so the domain for this one's actually really tricky, because trying to figure out the domain of this expression is a hassle. So this isn't just ln of x, this is ln of x squared, which means we need to consider whatever's in the parentheses. So remember, the domain of a logarithm in general is you take whatever the logarithm's evaluating, you set that strictly greater than 0, and you solve for x. Now here, what you end up getting, taking the square root will not show you the full extent of options. So what you actually get is x is greater than 0 and x is less than 0. And that kind of is derived from the plus or minus situation you get. The plus would give you the positive values, and the minus, well, the opposite. And so if you combine all of this, and that's why I'm showing you all this. This one's a pretty convoluted a domain-based problem. But when you bring all of this together, this gives you 0 to infinity. This one over here gives you negative infinity to 0. And you have to use the union here to attach all of those together. So this is definitely a more intricate domain-based problem. Again, that's why I'm showing you all it whenever you run into this problem on the homework. But that would be your answer for the domain. And finally, for part E, and to conclude this section, you're looking for f composed with h of e, the number e. So they want us to plug e into whatever function we got here. So instead of x squared, it's now e squared. But guess what? ln and e are right next to each other, so they cancel. Therefore, we are left with 2. And that would conclude this section.